So let's continue with section 2.3.4 of structure and interpretation of computer programs. And we have this example about Huffman encoding trees. So let's see. This section provides practice in the use of list structure and data abstraction to manipulate sets and trees. The application is to methods for representing data as sequences of ones and zeros, so bits. For example, the ASCII standard code used to represent text in computers encodes each character as a sequence of 7 bits. Using 7 bits allows us to distinguish 2 to the power of 7 or 128 possible different characters. In general, if we want to distinguish n different symbols, we will need to use log in base 2n bits per symbol. If all our messages are made up of the 8 symbols A, B, C, D, E, F, G, and H, we can choose a code with 3 bits per character. For example, log base 2 of 8 is precisely 3 because 2 to the power of 3 is 8. And so we only need 3 bits per character, for example, this one. And with this code, the message is encoded as a string of 54 bits. Okay? Codes such as ASCII and the A through H code above are known as fixed length codes because they represent each symbol in the message with the same number of bits. It is sometimes advantageous to use variable length codes in which different symbols may be represented by different numbers of bits. For example, Morse code does not use the same number of dots and dashes for each letter of the alphabet. In particular, E, the most frequent letter, is represented by a single dot. In general, if our messages are such that some symbols appear very frequently and some very rarely, we can encode data more efficiently, that is, using fewer bits per message. If we assign shorter codes to the frequent symbols. Consider the following alternative code for the letters A through H. With this code, the same message as above is encoded as the string, and we can see the string, that contains only 42 bits, in contrast with the previous 54. And so it saves more than 20% in space in comparison with the fixed length code shown above. One of the difficulties of using a variable length code is knowing when you have reached the end of a symbol in reading a sequence of zeros and ones. Morse code solves this problem by using a special separator code, in this case a pause, after the sequence of dots and dashes for each letter. Another solution is to design the code in such a way that no complete code for any symbol is the beginning or prefix of the code for another symbol. Such a code is called a prefix code. In the example above, A is encoded by 0 and B is encoded by 100. So no other symbol can have a code that begins with 0 or with 100. In general, we can attain significant savings if we use variable length prefix codes that take advantage of the relative frequencies of the symbols in the messages to be encoded. One particular scheme for doing this is called the Huffman encoding method, after its discoverer David Huffman. Huffman code can be represented as a binary tree whose leaves are the symbols that are encoded. At each non-leaf node of the tree, there is a set containing all the symbols in the leaves that lie below the node. In addition, each symbol at leaf is assigned a weight, which is its relative frequency, and each non-leaf node contains a weight that is the sum of all the weights of the leaves lying below it. The weights are not used in the encoding or the decoding process. We will see below how they are used to help construct the tree. So figure 2.18 shows the Huffman tree for the A through H code given above. The weights at the leaves indicate that the tree was designed for messages in which A appears with relative frequency 8, B with relative frequency 3, and the other letters each with relative frequency 1. Given a Huffman tree, we can find the encoding of any symbol by starting at the root and moving down until we reach the leaf that holds the symbol. Each time we move down a left branch, we add a 0 to the code, and each time we move down a right branch, we add a 1. We decide which branch to follow by testing to see which branch either is the leaf node for the symbol or contains the symbol in its set. For example, starting from the root of the tree in figure 2.18, we arrive at the leaf for D by following a right branch, then a left branch, then a right branch, then a right branch. Hence, the code for D is 1011. To decode the bit sequence using an Huffman tree, we begin at the root and use the successive zeros and ones of the bit sequence to determine whether to move down the left or right branch. Each time we come to a leaf, we have generated a new symbol in the message, at which point we start over from the root of the tree to find the next symbol. So now, since an image is worth 1,000 words, let's see at this figure to understand what all that wall of text means. So so at the root of the tree, the starting node, we have basically all the alphabet of our language, the A through H language. A, B, C, D, F, G, H, and 17 should be, I guess, maybe the frequency, the sum of the frequencies, because the text told us that A has frequency 8, B has frequency 3, and all the others have frequency 1. So 8 plus 3, 11, 12, 13, 14, 15, 16, 17. So this is the cumulative frequency. And indeed, in the first branch, we have just 8. We have just A with its frequency, and we have all the other letters with their cumulative frequency. And as you can see, 9 plus 8 is still 17. Then, if we branch again, you can see we split BCD, again the cumulative frequency is 5, 3 plus 2 plus 2, and E, F, G, H, each with relative frequency 1, and the sum is 4. And again, branch after branch, and it looks like, what's the splitting criteria for this tree? The splitting criteria seems to be the frequency that should be as balanced as possible. So as you can see here, we have 8 and all the others with a cumulative frequency of 9, and then we have multiple ways to split this right branch, and we decide to split in a way that on the left branch we have a cumulative frequency of 5 and on the right a cumulative frequency of 4. And then again here we can only have the only logic choice is to split between B, which has a cumulative frequency 3, a relative frequency 3, and C and D with a cumulative frequency of 2, and instead here E, F, G, H all have a relative frequency of 1, so we can split in an equal way so that we have E, F and G, H. And finally, we have the leaves of the tree with B and its relative frequency, and all the other symbols in the alphabet with their relative frequency of 1. Okay. So for example, suppose we are given the tree above and the sequence blah blah blah. Starting at the root, we move down the right branch since the first bit of the string is 1, then down the left branch since the second bit is 0, then down to the left branch since the third bit is also 0. And this brings us to the leaf for B. So the first symbol of the decoded message is B. Now we start again at the root and we make a left move because the next bit in the string is 0. This brings us to the leaf for A. Then we start again at the root with the rest of the string. So we move right, left, and reach C, and thus the entire message is BAC. Okay. Okay. Not sure. I have some dots, but I guess I will understand continuing to read. So generating Huffman trees. Given an alphabet of symbols and their relative frequencies, how do we construct the best code? In other words, which tree will encode messages with the fewest bits? Huffman gave an algorithm for doing these and showed that the resulting code is indeed the best variable length code for messages where the relative frequency of the symbols matches the frequencies with which the code was constructed. We will not prove this optimality of Huffman codes here, but we will show how Huffman trees are constructed. The algorithm for generating the Huffman tree is very simple. The idea is to arrange the tree so that the symbols with the lowest frequency appear farthest away from the root. Begin with the set of leaf nodes containing symbols and their frequencies as determined by the initial data from which the code is to be constructed. Now find two leaves with the lowest weights and merge them to produce a node that has these two nodes as its left and right branches. The weight of the new node is the sum of the two weights. Remove the two leaves from the original set and replace them by this new node. Now continue this process. At each step, merge two nodes with the smallest weights, removing them from the set and replacing them with a node that has these two as its left and right branches. The process stops when there is only one node left, which is the root of the entire tree. Here is how the Huffman tree of figure 2.18 was generated. Oh, I see. So you start from the bottom up to the top. I thought the process was exactly the opposite. Starting from the complete alphabet and instead of merging splitting with the relative frequency criterion, which is actually used, but with a different methodology. So the algorithm is starting from the bottom, starting from the symbols and merging them. And merging them. Mm, okay, I see. I see. Not clear why here oh, okay, I see. So here the first iteration is you are just merging C and D, then you merge E and F, then you merge G and H, and then again you merge EFGH, and at the following step BCD, and then you finally merge BCD with EFGH, and you obtain relative frequencies of 8 and 9. I see. The algorithm does not always specify a unique tree because there may not be unique smallest weight nodes at each step. Also, the choice of the order in which the two nodes are merged, that is, which will be the right branch and which will be the left branch, is arbitrary. In the representing Huffman trees, in the exercises below, we will work with a system that uses Huffman trees to encode and decode messages and generates Huffman trees according to the algorithm outlined above. We will begin by discussing how trees are represented. Leaves of the tree are represented by a list consisting of the symbol leaf, by the symbol at the leaf, and the weight. Okay. A general tree will be a list of a left branch, a right branch, a set of symbols, and a weight. The set of symbols will be simply a list of the symbols rather than some more sophisticated set representation. When we make a tree by merging two nodes, we obtain the weight of the tree as the sum of the weights of the nodes, and the set of symbols as the union of the sets of symbols for the nodes. Since our symbol sets are represented as lists, we can form the union by using the append procedure we defined in section 2.2.1. Okay. If we make a tree in this way, we have the following selectors. The procedure, symbols, and weight must do something slightly different depending on whether they are called with a leaf or general tree. These are simple examples of generic procedures, procedures that can handle more than one kind of data, which we'll have much more to say about in section 2.4 and section 2.5. The decoding procedure. As the following the procedure implements the decoding algorithm. It takes as argument a list of zeros and ones together with a Huffman tree. The procedure decode 1 takes two arguments, the list of remaining bits and the current position in the tree. It keeps moving down the tree, choosing a left or a right branch according to whether the next bit in the list is a 0 or a 1. This is done with the procedure choose branch. When it reaches a leaf, it returns the symbol at that leaf as the next symbol in the message by consing it onto the result of decoding the rest of the message, starting at the root of the tree. Note the error check in the final clause of choose branch, which complains if the procedure finds something other than a 0 or a 1 in the input data. Sets of weighted elements. In our representation of trees, each non-leaf node contains a set of symbols which we have represented as a simple list. However, the tree generating algorithm discussed above requires that we also work with sets of leaves and trees successively merging the two smallest items. Since we will be required to repeatedly find the smallest item in a set, it is convenient to use an ordered representation for this kind of set. We will represent a set of leaves and trees as a list of elements arranged in increasing order of weight. The following adjoint set procedure for constructing sets is similar to the one described in exercise 2.61. However, items are compared by their weights, and the element being added in a set to the set is never already in it. The following procedure takes a list of symbol frequency pairs such as A4, B2, C1, D1 and construct an initial ordered set of leads ready to be merged according to the Huffman algorithm. Okay? Bunch of exercises, a lot of exercises. Okay, I think I will stop here, and the next time we will read multiple representations for abstract data. So see you in the next video. Ciao, ciao.